And with that, I will go into talking about attention. So we talked about encoder-decoder models last time, where we have the inputs that go through the encoder and the outputs that are generated from the decoder. And when we create representations using this encoder-decoder model, as we talked about before, we had a single sentence representation that we created with something like a recurrent neural network. And we passed that on to the decoder that would then use it to do something interesting. And however, there's one problem with this. So there was a very famous talk about 5 years ago at the first workshop on representation learning for natural language processing by Ray Mooney, who's a very colorful character working on semantics. And basically the quote is, quote unquote, you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. And the idea behind this is basically you're taking a sentence which could be of arbitrary length or complexity, and you are converting it into a single vector. So instead of doing this, so you're trying to do something like the top thing here, where you take this as an example and you convert it into a single vector. However, another alternative is you do some sort of encoding, you do some sort of neural network to extract features from the sentence, but instead of trying to put it into a single vector, you instead convert it into multiple vectors that you can then use depending on your downstream task. So there's a couple reasons why you might want to do this. So in the end, a single vector is certainly enough to represent. So I don't exactly agree with Ray Mooney. A single vector is certainly enough to represent all of the meaning that you have in a sentence. And as a reason or as a justification for this, you could represent the entire sentence itself as just a vector of the integer IDs in the sentence if the vector was long enough, right? Or another thing that you could do is, like, let's say the maximum length of a sentence that you're using is 500 words. You could take all of these vectors representing all of the words in the sentence and concatenate them together, and that's a single vector, right? So the basic idea is you could take this sentence and turn it into a single vector. However, is that the most appropriate way of representing a sentence for downstream use? And one of the important things with respect to neural networks, like we talked about last time, is we want intuitive direct connections that allow us to take advantage of the pieces of information that we think we should be useful to avoid problems like vanishing gradients or other things like this. Also practically, like let's say you have a 1-word sentence and then you have a 80-word sentence. Does it make sense to represent both of them with the same size vector? Probably not, right? Because there's obviously a lot more information in the 80-word sentence than there is in the 1-word sentence. So that's the general idea here, which is instead of trying to represent a sentence as a single individually sized vector, we use multiple vectors that scale linearly with the length of the sentence. Pretty clear? Okay. So attention is a way to do that. And the issue, I guess, with using variably lengthed vectors in neural networks is up until now, if we wanted to pass this vector onto a recurrent neural network, we had a couple ways that we could do so, if you remember from the last class. One way was initializing the hidden state of the recurrent neural network with it, or doing some sort of transform or things like this. But either way, in LSTM, we'll always accept a vector of identical size. So we want some way of creating a neural network that can take vectors of variable size and still reference them with the same parameters that we have. And that's what attention allows us to do. So the basic idea of attention computationally is that we encode each word in the sentence into a vector of fixed size for each word. And then when decoding, we perform a linear combination of the vectors weighted by something we call attention weights. And we use this combination in picking the next word. So here's a simple example. Like, let's say we were trying to translate from Japanese into English, and we have an encoder that consisted of something like a bidirectional LSTM, and a decoder that consisted of something like a recurrent neural network, like an LSTM. And the decoder has already generated 2 words. It's generated I hate. And now we want to generate the next word in the output sequence. So what we do is we define a query vector, namely, in this particular case, the last vector in the decoded sequence, and some key vectors. And these are namely the vectors that we would like to be paying attention to, essentially. And for each query key pair, we calculate a weight. And we use some function. This can be any arbitrary function that takes in a query vector and a key vector and calculates a value from them. So we do that for the first pair, the second pair, the third pair, the fourth pair, and get these scores. And once we have these scores, we run a softmax over them to basically get something that adds up to 1, and all the values are between 0 and 1. And the basic idea here, kind of intuitively, is that this allows us to essentially weight the words in the source sequence and calculate a representation according to this weighted like mixture of the words. And specifically, what we do is we define vectors as value vectors. Usually these can be something like the encoder states, similarly to the key vectors, and take the weighted sum of them according to the attention weights. So we take these value vectors, we multiply them together with the weight here, and combine them into a single vector. And we can then use this vector in any part of the model we like. So the important thing here is, as I mentioned before, neural networks take in fixed size vectors, right? The parameter, like if we do a matrix multiply W times H, the size of the input vector is limited by the size of this parameter vector here. But by taking this weighted sum, it doesn't matter if the sentence is length 1, length 4, or length 50. The weighted combination of these value vectors is always going to be the same size. So because of that, we can use it in any part of the model, regardless of the length of the input sequence. Another nice feature of attention is that despite the fact that it's learned in an entirely unsupervised way, it can learn somewhat interpretable kind of weightings over the input corresponding to how important those inputs are at any for any particular decision we make. So this is an example of like generating French given English, I believe. And in this case, we can visualize the attention vectors so that the higher values are marked white and the lower values are marked black. And so we can see here when we translate le, it is focusing on the, or the gets the highest attention value, and all the way through the sentence. And we can see, even interestingly, French puts adjectives after the noun, whereas English puts adjectives before the noun, and the attention has figured this out and is focusing on the appropriate places. So I think this is nice in a couple ways. Number one, it's a pretty good model. And the reason why it's a pretty good model is because it doesn't require you to, before you even start decoding, to generate a single vector that captures the entire meaning of the sentence. Rather, you can step through the sentence word by word, and at every time step, choose the content in the original sentence that's most important for you. So for translation, you know, you need to leave around, you need to focus on kind of basically every word in the sentence to do a good translation. But if it's something like summarization, for example, you might not even need to focus on some of the words, but you can focus on only the words that you are most interested in outputting it throughout the sentence. Any questions? All set? Okay, so I kind of skipped the part where we actually mentioned the attention score function. And the attention score functions, you could choose any number of them. Q is the query, K is the key. The original attention paper for machine translation used a multi-layer perceptron where basically you concatenate the query and the key, you multiply them by a weight matrix, do a nonlinearity, multiply them by another weight vector, and that gives you the score. This is a flexible method that is often good with large data, but there are other options as well. Another one is the bilinear function, where the bilinear function is basically multiplying the key with a weight matrix and then multiplying that together with the query. And another thing that you can do is just take the dot product between them, between the query and the key. This is reasonable, but it requires the sizes of the query and the key to be the same because you can only take the dot product between two vectors that are the same size. It also requires the query and the key to be in the same space. And there's also something called the scaled dot product. And one problem is that the scale of the dot product increases as the dimensions get larger. And one way you can fix this is scale this by the size of the vector. So if you're taking the dot product between the query and the key, you take the square root of the length of the K. This could be K or Q because their lengths are the same, so it doesn't really matter which one you pick. But you scale it by the square root. And this is also similar to the idea that we had before with initializing the parameters using Glorat or He initialization, if you remember from a few classes ago. Basically, as the vectors get larger, the scale will get larger and things will get more peaky. And the reason why scale is important is basically if you take, like, let's say we have 1 and 0.1, and we run them through the softmax, we'll get something like 0.75, 0.25. But if we take 10 and 1, it will be like 0.9999, 0.0001. And if the attention values got this extreme, then this would basically make it harder to learn because you would be putting all of your attention on one word and not the other. So that's why we do this scaling to kind of make sure that the input values don't get too extreme. So I had a question. Can I elaborate on what you mean by Q and K need to be in the same space for the dot product? Yeah, so that's a good question. When you're taking the dot product, basically, when we're calculating the values here between the query vector and the key vectors, if we're just taking the dot product between the query vectors and the key vectors, the query vector and the key vector will need to be similar in order to get a high attention weight. So let's say the key vectors are in Japanese and the query vectors are in English. That would mean that the query vectors and the key vectors that so basically, in order to get a high attention weight, query vectors for the decoder state in English and key vectors for the encoder state in Japanese would have to be similar in order to get a high attention value. And now this is kind of a high order, right? Because we're also asking the decoder to do other things like track where we are in the sentence, or keep track of all of the content that we've translated already, but not the content that we haven't translated yet, and other things like this. So in order for these to be, in order for them to do that at the same time as basically, you know, keeping it close to the key vectors in order to do good attention is kind of a high order. It's kind of a high expectation to be putting on the network. So does that more or less answer the question? Okay, cool. So yeah, these are the various ways we can calculate this function here. Are there any questions? Okay. So another important concept in attention is self-attention. So I gave an example here of when we would be doing attention on the input when we're generating an output. This is now called cross attention. So it's attention across two different types of sequences, basically. Self-attention, on the other hand, is when you are doing attention on the sequence itself. And this is one example. If we have this is an example, we might want to calculate the value of this, or the vector for this. And what we could do is we could attend to this is an example and take the weighted average of these vectors here to calculate the value of this. For is, we might take calculate the attention values, take the weighted average, other examples like this, and example. And just to give a kind of motivation for why this might be useful, when, let's say we wanted to later use these self-attentional encodings in a translation system or something like this, if we wanted to translate this pronoun into another language, like, does anybody speak like French or Spanish or something like this? Okay, so if this was example, how would we translate this pronoun in? UN, and like, let's say it was something else, like table or, yeah. So the difference, there would be a difference for how you would translate this based on what the name of this noun would be. And so basically by combining together the representation for and, which of course we don't want to forget, with the representation for example, that would help disambiguate whether you would translate that pronoun into masculine or feminine. And there's lots of other, you know, examples like this, like the word, a light verb like have is translated very different ways if you do things like have a party, have a blast, have a Coke, or something like this. So in order to do that, you would need to combine the representation for have with the representation for something else. So then the question is, I had a question on Zoom, how do you get the vector for is to use in creating this vector if the is vector hasn't been created yet? It will be created using the new this vector, right? So yeah, that's a very good question. So basically, I could go into a lot more detail in this. There's a more general idea of like synchronous versus asynchronous computation, like what order do you calculate these representations in? But basically, long story short, you start out with just context independent word embeddings. So you have a word embedding lookup like everybody did in your homework. So you start out with the context insensitive word embeddings, and then you run it through multiple layers of this self-attention to get the final representation. And in every layer of self-attention, you use the previous layer. So you start out with context insensitive in layer 0. You calculate the representations for layer 1, given the layer 0 representations, and they calculate the representations for layer 2 using the layer 1 representations. Okay. So this is a very important concept. This is used everywhere in NLP nowadays, BERT, transformer-based translation models, whatever. So important thing to know. Any other questions about this? Oh, to do this, do you just do exactly the same procedure as presented earlier, but just have the same sentence as input and target sequence? Yes, basically. Yeah. Okay. So another very important concept to know about is something called multi-headed attention. And the idea behind multi-headed attention is that in all of the examples I've given so far, we've had a single attention weight for basically every combination that we want to do. So if we want to calculate the representation of this in a particular layer, we always will have a single vector corresponding to the inputs here. Multi-headed attention relaxes this restriction and basically allows you to have multiple attention weight vectors for at a single time. And these multiple attention heads focus on different parts of the sentence. So one example of this that's particularly, I guess, like intuitive, and this is the reason why I like to present it first, is if you had a model that had the ability to copy, like what I talked about, like what I'll be talking about in the future, you might want to have a model that focuses on different words when it is attempting to copy a token from the input to the output than when it is just attempting to use, like, calculate representations to decide which word to output or something like this. So in this particular example, they train a model that that has one attention vector for when you're copying words and one attention vector for when you're just calculating the representations of the words for the decoder. Another example, which is used in transformer-based models, which we'll be talking about in more detail in a second, is you basically just train multiple heads. You initialize them randomly, you train them independently, and you hope that they discover different things. So you might train 8 different attention heads with the idea that they will discover different phenomena. And this is an example from a translation paper where we have the word making. And when you are calculating the representation for the word making, you have one piece of the representation come from the previous word, one piece of the representation come from the current word. And actually the current word is always passed through to the output using a residual connection. So basically it's passing through information for the current word by default. So the fact that there's only one attention head focusing on the current word is kind of like deceptive, I guess. But then the remaining attention heads are all focusing on the subject of this verb here. And this actually exactly reinforces what I just said about light verbs, right? Making is another example of a light verb that has many different meanings depending on its context. So in order to disambiguate the word making, you really need to know what you're making. You need to know you're making something more difficult instead of making a cake, for example. So it makes sense that you would be focusing on all of the outputs here. So there's actually a good visualization of this. Let me see if I can pull it up. So I will show it on the screen. And also, and if you want to search for it, it's called BERT-Viz. It's visualizing BERT, which also has multi-headed attention included in it. And you can look at different layers and see that the cat sat on the mat, the cat lay on the rug. It's actually kind of hard for me to see from here. But for example, let me look at layer 1. Is that really light for you guys as well, or is that just hard for me to see? Okay. Okay. But anyway, like for we can see it's focusing on cat. We have the green and red attention head that are kind of focusing on cat. For cat, we have the red attention head is focusing on sat. For sat, it's focusing on. So you can kind of see this red attention head is just focusing on the following word. So you can see it's learned one attention head that focuses on the following word. We have another attention head, this blue attention head, that focuses on the determiner corresponding to the word. So you see the blue attention head, or no, sorry, the blue attention head is focusing on the previous word. So we have one attention head that focuses on the next word, one that focuses on the previous word. So it's basically encoding the immediate context around you. And then you have other attention heads that are doing more interesting things. So like, for example, here, rug, you can see the yellow attention head is focusing on lay. So it's focusing on the verb, for example. So that's the kind of power of multi-head attention. It allows the model to not just learn a single thing, like you should be focusing on an individual input, but also focus on different types of phenomena depending on the type of head you're using. And so the way that this is done standardly here is basically you divide up the input vectors into, n different segments, and you have each segment calculated an attention head for it. Actually, if I have time, I'll do a quick code walk at the end to show exactly how this is done computationally. So we can look at more detail later. Is there a way to enforce the different heads in an independent setup to learn focus on different attributes? That's a question from Zoom. Yes, there is. And that's actually a very good question. There's a couple ways to do this. The first way to do this is if you know what attributes you want the model to be focusing on. You can enforce this through supervision. So here's an example of a paper that does this. Oops. Here's an example of a paper that does this where they explicitly tried to enforce the model to focus on syntax, on other words that were in a syntactic relationship through dependency parsing. So we're going to be talking more about dependency parsing later. Another thing that you can do is if you want to get it to focus on different things and you don't really care what they are, you want to focus it to have like kind of capture different traits for each of the attention heads. There's a way to do that as well. I actually, I might not be able to find the paper immediately. So if there's any interest in that, please follow up on Piazza and I'll find the paper and send it along. So very good question though. Any other questions? Okay. Yeah, if you take this to the extreme, you could have one attention head for every hidden node in the input. So like if you had 512 nodes in the input, you could have 512 attention heads. So you can kind of see multi-head attention as a kind of extreme from regular attention with one to having a single one for every node. However, this is extremely computationally inefficient, so nobody actually does this in practice. Okay, so in terms of an interesting case study, this is a paper, Attention is All You Need. It's a paper for transformers, which I think a lot of people have probably heard about. And basically, this is the kind of famous model that is used in a lot of different NLP models nowadays. And this is a fully attentional model for either encoding or for use as an encoder-decoder model on the right side. And it has several components. We can start out by looking at this architecture diagram. I think one other major contribution of this paper is they have a nice architecture diagram like this that now everybody copies. So it's very easy to see what other architectures are doing, and their color scheme is not ugly. So that was a good contribution as well. Although this projector is very washed out, it's hard to see. But so what we do is we have our input and output embedding. This is what I was talking about before, the non-contextual embeddings for each of the words. We add something called positional encoding, and positional encoding is important. I'll explain a little bit more about it in a second. Then we have n of these blocks, where these blocks are called transformer encoder blocks and transformer decoder blocks. A transformer encoder block has a multi-head self-attention here. So it's doing the multi-head attention that I just explained about in a self-attentional fashion. It also does addition, and so this addition is a residual connection where basically you are doing so the output xt plus 1 is equal to this. So this is like the LSTM, right? So the reason why we did the LSTM was because we wanted to allow gradient flow all the way from the end to the beginning through additive connections. And so the residual connection does the same thing for us. And it also has layer normalization. And basically what layer normalization is doing is it's taking the output and it is multiplying the output by a constant. Let's call this v for variance, or your corresponding to the variance, and then you're adding another constant corresponding to the mean. And they actually probably, if we're going to talk about it as variance and mean, you're dividing by the variance and subtracting the mean, and this kind of makes normalizes the outputs into a reasonable range. So it would have like 0 mean and unit variance. In reality, you actually learn these parameters, so it's not quite as simple as that. But the basic idea is that you're trying to normalize the outputs of the model so they don't get too crazily large or crazily small. So that's also very important. After that, we have a feed-forward network, and usually the feed-forward network is very large. So what we're doing is we're taking the self-attentional vectors. We're projecting them up into a very large vector, running a nonlinearity like a ReLU, for example. And then we're projecting them back down into our regular dimensions. And what this is doing is this is allowing us to learn feature combinations. And we talked before about how important feature combinations are. So this is extracting combination features from each of the attention-derived feature vectors, and then projecting them back down. And again, here we have a residual connection and a layer normalization. So this is the encoder, the transformer encoder. So are there any questions about that part? Okay. And then for the transformer decoder, we have self-attention, multi-head self-attention. And basically what this is doing is attending to the previous time steps. And then we have multi-head multi-head cross attention. So this is kind of like the traditional attention that I talked about, where we're attending to the things in the other sequence. And then we have a feed forward layer. So basically the decoder, there's two differences from the encoder. One is that we are doing masked attention, only attending to the previous time steps. And the other thing is that we're also attending to the input sequence here. And actually, maybe I'll talk about the mask here. So basically what the mask looks like is when we're doing self-attention, we, on the decoder side, we only attend to previous things. So in the first output here, we don't attend to anything. In the second output, we only attend to the first one. In the third output, we only attend to the previous one. And this is to ensure kind of the autoregressive property, ensure that we actually are predicting the output based only on the previous outputs instead of conditioning on the next outputs by mistake. And then in the end, we can have a linear layer, a softmax, and calculate the output probability. So that's just like what we had previously in our language model or something like this. So what is the positional encoding here? The positional encoding is necessary in a model that is entirely based on attention. And the reason why it's necessary is, let's say we didn't have any sort of recurrent neural network or any other thing, and we just want to rely entirely on attention. And we have a sentence like the cat sat on the rug, like the example that we just had. Here, we have two thes, and at the very beginning, when we look up our context insensitive embeddings, these thes will have the same embedding, of course, because they're the same word, right? And if we don't have any way of distinguishing between them, they would get the same vector all the way through the computation. So they would get, we would do attention, they would get exactly the same self-attention weights over the entire sequence because they're the same vector, and then they get the same vector through every other layer of the output. So what positional encodings do is, in addition to like the encoding for the word the and the encoding for the word cat, the encoding for the word sat, they also have a separate encoding, a separate embedding for, this is the first word in the sequence. This is the second word in the sequence. And this is the fifth word in the sequence. And then you add these two together. And because you add them together, now instead of having just W the, we have W the plus W1 and W the plus W5. So now you can distinguish between these two words. And there's different ways of calculating this positional encoding. In the original transformer paper, there was this kind of crazy, like not very well described sinusoidal function and cosine function way of calculating these embeddings, these positional encodings. There's actually a lot of reasoning, or there's actually reasoning behind this, which is that if you use these sinusoidal functions, it allows you to calculate similarity. After taking a linear transformation, it allows you to calculate similarity between things of different like distances from each other. But a simpler way to do this that's used in a lot of more recent models is to just train the positional embeddings together with the model and allow them to find it. I saw two hands at the same time.
Why do we add the positional embedding?
Why do we add them instead of concatenating them? That's a good question. So one thing to know is that the positional encodings and the input embeddings both go through a linear transform after this. So basically, after we calculate the embedding, let me call it E. Actually, E would be a better thing. So E. We have the embedding, and that gets multiplied by a matrix to calculate the query and the key for attention. And if you concatenated them together, basically what you would need to do is you need to make this weight matrix twice as large, or at least the size of the positional encoding plus the size of the original word embedding. That's completely possible, but it would require you to have a larger weight matrix here, and it's more expressive, but maybe less efficient. So you could do either if you want.
Is the positional encoding learned with the training thing? Do you always have a fixed position like this?
So you could do either. You can either learn the positional encoding together with training, or you can have some way of pre-computing it, like the sinusoidal thing that I just mentioned. Yeah, so there's different ways. There's also other ways of like pre-computing it using like a mathematical formula. Yeah.
So this works. Do you have a sense of like how the model is?
So that's a very good question. Do we have a sense of how the model disentangles position versus semantic content? This is a good question, but it's also kind of vague, I guess. Not like, not to be like disparaging or anything like this. It's just kind of a vague question. So I guess it would depend more on what your concrete question would be there. There is some, like, just to give an example, my impression is that a lot of the self-attention, sorry, I closed the window, but a lot of the self-attention patterns, like the ones I showed in BERTviz, are very much based on position. So they're based on the previous word, the next word, etc. But on the other hand, a lot of them are based on, like, is this the verb in the sentence? Or, and other ones are based on both. Like, if you have a very long document, it will tend to focus on the words that are close together with you, but it will also focus on the verb of the sentence or something like this. So I think for sure, it is, transformer models are able to consider both of them at the same time to decide what is the most important thing to be focusing on. So I saw another hand, but yeah. Uh-huh. Oh, yes. Yeah. Mm-hmm. Okay. Yeah, actually, so that's a very good point. And sorry, I should have pointed that out more carefully. So these lines indeed are representing the queries, the keys, and the values. So in multi-head self-attention, in self-attention, the queries, keys, and values all come from the same place. So they all come from the same place, but actually in the transformer model, I should probably have mentioned this explicitly, but the transformer model is using something they call dot product attention, but it's actually bilinear attention. And what I mean by this is they are multiplying the input embeddings by a weight matrix, and then taking the similarity between them to calculate the key and the query values. So basically, because you're multiplying by a matrix, it's bilinear attention, and then they're scaling it according to the scaling function that I talked about before. So where do they get the inputs to the key for the key and the query and the value that are going to be multiplied and then compared together? They get them in this particular case, they get them all from the same place. They get them from the input here. For multi-head attention here, the keys and the values they get from the input, and the query they get from the output. So I think basically the last one is corresponding to the query. Yeah. I have two questions on Zoom. Are we inducing some sort of ordering between the repeated words using numerical position embeddings? If so, is that desired? So the numerical position embeddings, yeah, I think basically it is inducing an ordering. It's giving information about the ordering of the input embeddings, and it's using that to learn things like things in the same local area are more likely to attend to each other and things like that. And so I do definitely think that's desired or intended. There might be better ways to do it, but that's the short answer, I guess. So regarding the concept of multi-head, multiple attention heads, in the single self-attention case, we compute a score between every pair of words, and then every word is represented by a linear combination of all vectors. How does this concretely change when going to multiple self-attention? So yeah, actually, that's a very good question. Maybe I will. Let's see. Okay, so maybe I'll just write it on the board here. But basically, the idea is like, let's say we have H T, which is the input to the transformer. And I'll talk about self-attention here just because it's simpler. But what we do is, like, let's say we have 8 attention heads. We'll basically partition this vector into 8 pieces, and then do self-attention over like all of these pieces separately, where the parameters for the first one, the parameters for the second one, the parameters for the third one are all different, basically. And this self-attention is done independently, so it's done independently for each of the pieces here. But an important thing to pay attention to is, despite the fact that this self-attention is done independently, after that, we're feeding it into a big feed-forward network, which allows you to create combinations of features across the whole vector. So you do the self-attention independently, but then combine the features together across the whole vector using the feed-forward network. For the learned positional encodings, you learn an embedding vector for each absolute number. Yes, exactly. So would really large numbers get undertrained? Yes, that is true. And I think this is not a problem. Let me put it that way. So to use a double negative, like I think that could cause degradation for longer sequences. However, despite the fact that they may be undertrained, they'll be less undertrained than, for example, really rare words, right? Because really rare words will occur much less frequently than long sequences. So my personal impression is that it's probably not a huge problem, but I could be proven wrong, I guess. So, there was a question when first talking about transformers. One of the heads attended to the previous word at each time step. How can an attention head know which word is the previous one so that it can attend to that? Isn't the same function applied to all words in the sequence? Is it somehow because of the positional encoding? Yes, that's a very good question. It is because of the positional encoding, and basically what you can learn to do, I'm not going to be able to accurately do all the math up here, but what you can learn to do is we have a key vector and we have a query vector. So the key vector, or just to give an example, like let's say the query the weights into the query vector, manipulating the query vector just became the identity and didn't make any changes. This key, the weights for calculating the key vector here would then need to manipulate the weights in a way that would move them close to the previous word, for example. So this transformation here would have to switch the positional encoding from W2 to W1. And that's not necessarily, or that's a thing that's possible using either the pre-computed encodings, because they specifically designed them in a way that makes that possible. Or if you had learned encodings, just to give like one trivial example of how you could do this. Let's say the learned positional encodings were like 1 for E1. And then something like this, where basically the each encoding had a one-hot vector in each encoding had a one-hot vector in the appropriate position depending on what vector it was. All you would have to do is you'd have to learn a linear transform that shifted the vector up by 1, which is a trivial thing to do. So this is something that you can easily learn when you're comparing the like multiple positional encodings. Okay, very good questions. Thank you. Any other questions? Yeah.
So in this diagram, we have the output. How is it work during test time?
Oh, very good question. So in this, here we have the output embedding. What do we do at test time when we don't have the output embedding? So basically, long story short, at test time, in the first sequence, like if you're actually doing translation, sorry, this is a little bit confusing. I should have actually added it here, but you would usually pad the sequence and move it to the right by 1. And because you would pad the sequence and move it to the right by 1, you would feed in basically the beginning of sentence here. I should fix this later to make it more clear. But the first time you basically have a sequence of length 1 with just the beginning of sentence. Yeah.
For the sample that you gave, why don't those have the same embedding after training, even without the positional embedding? Because the representation is dependent on the context, right? Because they are coming in different contexts, they should have different representation.
Very, very good question. So would these have the same representation because they appear in different contexts? So they, in the very first layer, they will have the same representation, because the very first layer, you are just feeding in context independent input embeddings here. So the will be just something you look up in a table like you did in the homework assignment. If you have the positional embeddings or positional encodings, after the first layer, these will be different, right? Or after you add in the positional encodings, they will be different. However, if you don't have positional encodings, basically in multi-head self-attention, they will be assigned exactly the same attention vectors, basically. So the linear combination of the outputs will be exactly the same. This feed-forward network is applied position-wise, so it's only applied. It's applied to one position, like the first position, the second position, third position independently. So that also won't change the encodings. So after each transformer block, if you don't have the positional encodings, there's still no way to distinguish between them. Okay, great. So yeah, I actually already talked about most of these. one other thing to note when you're using transformers is this paper, when it first came out, my impression is like, wow, this is an amazing paper. It's really great. And I read it in our reading group and was excited about it. But at the same time, up until this point, everything was based on RNNs, and then they created a model that worked entirely using attention. And they obviously really wanted to do this. They really wanted to show that attention was all you need, and they did that successfully. But at the same time, in order to do this, they also added a whole bunch of tricks. So layer normalization is very important. They also have a specialized training schedule. It's called the Noem training schedule, colloquially after Noem Shazir, one of the authors. And basically what it does is it uses the atom optimizer, but it like phases in the learning rate at the very beginning and then gradually decreases it later. This is very important because transformers are more difficult to train than RNNs. So if you don't do this, basically they'll get into a very strange space at the beginning of training and not be able to recover. They also use something called label smoothing. So label smoothing is a trick that is very useful for getting good, for getting like small but consistent improvements. And basically what it does is normally when you're calculating the like the log likelihood of the output, you do it by multiplying the model probability like 0.01, 0.05, 0.01, 0.03. You take the dot product between this and a one hot vector representing the correct answer. Sorry. So, and then you take the negative log of this, and this is your loss function. So basically, what this results in is this results in the probability of the correct following next word, the correct following next answer. What label smoothing does is it slightly smooths this this target vector that we're using, and adds a little bit of probability to all of the wrong answers. I'm not going to go into a huge amount of detail now because there's lots of explanation online if you want to see it. But basically, what this does is this prevents the model from like being too confident in its answers when its answers are not actually likely to be correct. So this is another trick that they added. And they also did masking, which I talked about before. But basically, long story short, the fact that the transformer models gave very impressive results in the paper that they had here was a result, number one, of it being a good model in general, but also number two, of all the engineering tricks that they did to make it actually work. So I think that's important context to have. And also, like, you need to know about things like the specialized learning rate schedule, because if you don't use this, then it will die and not help, not work at all for you. So great. Any other questions? I think I might have to leave this code walk for everybody to do on your own. I highly, highly recommend this though. And basically what it is it is a blog where a blog by Sasha Rush, who was at Harvard then, he's at Cornell now, where he basically took the paper and he took excerpts of the paper and turned all of them into code, block by block. So you have excerpt from the paper and then code, excerpt from the paper and then code. And it's really informative in understanding the things. And your next assignment is actually going to be implementing transformer blocks. So this is a good reference for you to take a look at. Okay. So yeah, just to give a caveat, like I mentioned before, transformers are very popular. So they're popular for performance. And when I say performance, I mean both with respect to accuracy and with respect to speed. So one thing I forgot to mention, although I had it written on the slides, is transformers, especially at training time, can be calculated purely using matrix multiplies. So basically, you do a matrix multiply to calculate the key vector, the query vector, and the value vector. And then you can calculate this for all of the words in the sequence in a single pass, in a single GPU call or TPU call. This is in contrast to recurrent neural networks, where the representation of the next word relies directly on the representation of the previous word. So you basically need to calculate them in serial. So the number of operations that you can calculate at one time is limited to basically the number of sentences that you have in a batch. So transformers, from that point of view, are very fast, especially if you have a fast computation engine like a TPU or GPU. One other thing is transformers can be slow to decode at test time. So basically, in order to decode with a transformer at test time, you have to recalculate all of the representations in the output sequence. And this can be an issue if the output sequence becomes very long. Like, let's say you wanted to generate a whole document from a language model. Basically, your decoding time is quadratic in the length of the sequence instead of linear. Another thing is actually, despite the original flashy results, in fair comparisons between RNNs and transformers, especially as decoders in sequence tasks, it's not super clear that transformers are actually better accuracy-wise. That being said, they're a lot faster, especially at training. So that's something to be aware of. But if you want to learn more about that, you can look at this paper that has that comparison. Another issue is that transformers can be harder to train on small data. So if you have small data, RNNs can do better. They're definitely a tool that you'll need to have. They're used in most modern NLP, but you can also be aware of the limitations. Okay, any questions? Cool. So this is the main content of the lecture up until now. I have a few kind of extensions for people who are interested in topics, in extra topics. So there's a lot of things that you can do to improve attention. So like one example is incorporating kind of biases into your attention based on your intuition of what kind of things should be useful. So for example, we might know that attention should in general be correlated with attention that you did in the previous time. So for example, if you know that the model attended to this last time, you might think it wants to attend to the next thing. So you can add information about the previous attention that you've done when you're making your next decision about where to do attention. So that's described in this paper. Another thing that people have used pretty frequently is something called hard attention. So normally attention is a soft process where we run through the softmax and do a combination of the softmax outputs. But we can also make a 0-1 decision about where to attend. The disadvantage of doing this is that this is harder to train. So it requires methods such as reinforcement learning, which we'll talk about in later classes. But there's also advantages to this. So there have been reports that this can help with interpretability. So for example, let's say we wanted to train a model that like explicitly extracts a particular part of the information in the input and presents it to a user. In that case, it might be useful to do it in a hard fashion instead of a soft colored fashion. Another thing is for some tasks, we know with some certainty that they are going to be, the output's going to be in the same order as the input. An example of this would be something like speech recognition, because in speech recognition, we know that basically the output words are going to be in the same order as they were spoken. So we can do things like basically enforce that the attention will always move to the right. So this is kind of like a harder constraint than the Markov property that I talked about before. Some other things that we can do. Coverage is a very important topic in some areas. So one issue with neural models is that when they're well trained, this doesn't happen very often. And in fact, transformers have fixed this issue to some extent. But when models are poorly trained, they can tend to drop or repeat content. So they will drop some parts of the input or repeat some parts of the input. And one thing that we can do is model how many times words have been covered. So for example, imposing a penalty if attention is not approximately 1 over each word. So this is useful for things like machine translation, where we know that each word should be attended to approximately once in the output if there's a 1-to-1 correspondence between words. We can also add embeddings indicating coverage. So if there's, we can indicate how often words have been covered. Another method is bi-directional training. So if we're training like a translation model, we might know that the attention in one direction should be similar to the attention in the other direction. So to take an example here, we have attention in one direction and attention in another direction, and we would like them to overlap. And so the way we can express this is basically we multiply the attention matrices together like this, and we take the trace, and this trace will be higher, I believe. Yeah, I think higher if they overlap. And we've also, I don't have this on the slide, but I can share details if people are interested. But recently, one of the students I was working with, Junjae, who incorporated this in learning of multilingual representations with transformer models, and it also gave a good effect there as well. Another thing that you should be aware of is that attention, there's an idea of alignment in, for example, translation or summarization or other things like this, which is like which content corresponded to the content we are outputting on the output side. And I don't know how many people here used Google Translate long enough ago to remember this, but about 5 years ago, Google Translate would actually allow you to mouse over the output and see which input generated the output. You can't do that anymore, or at least as of the last time I used Google Translate, you couldn't do that anymore. And the reason why is because attention doesn't give you a good enough concept of what is aligned from the input. And it's even harder in transformers, right? Transformers have 8 heads. Which head do you use to express this alignment? And this is one example from a translation model, which was trained with single head attention, but nonetheless had a one-off error where basically the attention was one off of the actual alignments here. So there's even some recent work that demonstrates that attention can be manipulated to be non-intuitive. So you can train a model that intentionally doesn't attend to the information that's most useful in making a decision, but nonetheless achieves high accuracy. So like you'll often hear people talking about attentional explanations or like using attention to interpret your models, but there's absolutely no guarantee that you can actually do this, right? However, let's say you wanted to create a model where attention basically did correspond to alignments, for example, because you wanted to implement a Google Translate style, alignment to the original input. And one very easy way to do this, which I know is used in some commercial systems as well, is you get a small number of gold standard alignments, like you ask a human to create alignments for you. And you could also potentially get these alignments with an alignment model, but like, let's just assume you have manual alignments. You can train the model to match these strong alignments. So it's basically, you have a loss function that encourages matching with the alignments. Okay, and the final part is copy mechanisms. I alluded to them briefly before, but these are very important things in any task where you are able to copy content from the input to the output. So this won't work for something like Chinese English translation, or no, maybe it would, even Chinese English translation, but it wouldn't be as good for something like Chinese English or translation, because very few words would be copied from the input directly to the output. But for something like summarization, most of the stuff you'll be creating in the output would be copied. So basically, we have a copy mechanism, and what the copy mechanism does is it attends to words in the input sequence, and then it has something that allows you to choose, when I generate the next word, am I going to generate it through copying content from the input, or am I going to generate it from my vocabulary? And there's a few different details about how exactly you do this, but that's a basic idea. You have one decision about whether to copy or not, and another decision about what words from the vocabulary you create or what words from the input you copy. You can also copy from the already generated things. So this is, for example, in language modeling, once you generate a word, you're much more likely to say it again. So if you think about a news article, Fed Chair Janet Yellen are the first words in the sentence, you're much more likely to say Yellen somewhere else in the output. So you can copy directly from the words you've previously output. Another thing that you can do, actually, this is nice work. It's my work, but I'll skip it in the interest of time. So you can talk more about it if you want to with me in office hours or something. And another thing you can do is hierarchical attention. So there's actually a bunch of different forms of this now, like sparse attention or other things like this. But hierarchical attention, basically what it does is it has a lower level attention that generates a vector, and then you have a higher level attention that uses the generated vectors. So one typical example of this would be attending to the words in a sentence to create a sentence embedding, and then attending to the sentences in a document to create a document embedding. And then you can also do attention over images, speech, etc. And then the final thing is multi-source attention. So this is also a common thing to use. You can basically have sentences in multiple languages, attend to both of them and generate the outputs, or attending to like a sentence and an image to do multimodal translation or other things like this. So these are all examples. And yeah, that's all I have for now. Are there any final questions before we wrap up? Or yeah.
Sure, using multi-source or anything, but with one context that is not that good, like the keys are not that good. With the softmax, you will sum everything to one, so it will recount anyway. Like even if all the weights for cosine are negatives, it sums to one. And is there like sometimes we should take review or other things in order to get rid of?
So that's a really good question. So if you have something where basically none of the attention values are high, should you attend to it? There is sigmoid attention, where sigmoid attention basically decides whether you attend to a particular thing or not, or whether you attend to anything or not. Empirically, softmax attention seems to work much better. I've seen this multiple times, so I think it's not a fluke, but I think it's possible that you could have some sort of thing like softmax attention, but with an additional gating to tell whether you would pay attention to the like attention at all. I don't know if that exists. It might, but I don't have any reference for it now. Good question. Cool. What is the intuition behind RNNs transforming better than performing better than transformers on small data sets? It's basically, it's a good question. I think RNNs basically have a stronger locality bias, for example. So it's easier for them to learn things like neighboring elements are important. I actually don't know a good answer to that though. That's a good question that I should know the answer to, but I don't. So great. Yeah, thanks a lot, everyone. I think I'll finish up here, but happy to take any questions up front.